the molar solubility of iron 2 hydroxide in pure water, there's the KSP. Okay, so we're doing solubility. That means we're taking this solid and we're going to break it apart into ions. So this is a dissociation equation. And yeah, it's equilibrium. So iron and 2 hydroxides. Make sure that you get the coefficients here, because when we're doing this solubility, the coefficients matter. Now, the way the book teaches this is, instead of doing it with X's like we have been, you can do that if you want to. You can use, it uses S's. So that was what I did in my handouts to stay consistent with the book, because I did not want to be overly confusing. But this is a solid, so it doesn't matter in equilibrium. We know that when this dissolves, initially, we're going to have none of it. And then when this dissolves, this is going to be 1 S for solubility. These are S's, not 5s, so that's why X's tend to work better for me. And this one, when it dissolves, we're going to get 2S. So at equilibrium, we have S and we have 2S. So now let's write our expression for our solubility product. Solid doesn't matter. So we're doing products over reactants. So Fe plus 2. And here you have OH. The coefficient becomes the exponent and it's squared. So plug and chug here. 4.87 10 to the negative 17th is S times 2S squared. Remember your laws of exponents when you do this. So that's S, and that is 4S squared. You have to square the 2 as well. 4.87 10 to the negative 17th. So that's 4S cubed. So if you can type this in the calculator all in one step. So 4.87 10 to the negative 17th. I'm going to divide by 4 first and then take the cube root. It's easier for me to do a 1/3 exponent. Means the same thing. So you get 2.3 times 10 to the negative 6, and that's going to be a molarity. And you can say equals solubility, or you can just circle it. Yes. On there, when you add the 20 milliliters, you should get pH is 12.32, and at 25, you should get pH is 12.67. Here, you're I've got enough time, so let me go ahead and run through this one. It's mostly it is going to be the same. Here we've gone past equivalence, so you don't have to do a Henderson-Hasselbalch as much, because you're going to have excess base. When you have excess base, weak base and strong base, strong one dominates. So here, hydroxide plus, I'm just going to write this as a generic acid because I'm tired of writing it. It's just a shorthand. That's going to give us water and our conjugate base. All right, so the starting amount of the acid is still the same. So what was that? 4.95. Make sure I got that right. 4.95. And here we're going to have 6 of the hydroxide. Now in this case, the smaller one gets used up completely. So that's minus 4.95 minus 4.95. That goes away. For completeness, you can put plus 4.95, but it's not going to matter because this is a weak base. This is a strong base. The strong one is what really matters. So 6 minus 4.95, 1.05, 1.05 millimoles. So we need a volume. Here we have 20 milliliters, and we started with 30 milliliters. So 20 plus 30 is 50 milliliters. 1.05 divided by 50, 0.021. 0.021 molar OH minus. This wants to know the pH. This is a strong base, so this one doesn't matter because it's a weak base, so it gets dominated by the strong one, just like a strong acid dominates a weak acid when it comes to pH. If you really want to do an ice table with it, go right ahead. It's not going to matter. Take the shortcut. So here I'm going to do POH, negative log of 0.021. So negative log that, 1.68. Let's subtract 14 minus that, pH 12.32. Same process for this one. Only instead of 6 millimoles, you're going to have 25 times 0.3. So what is 25 times 0.3? 7.5. Plug 7.5 in for 6. Same process. That'll work. Last call. $16. Oh, this is a fun one. I like this one. All right. All right. So here, this question is asking, see here it tells you the answer to the first one. So this says our magnesium hydroxide is going to precipitate out. However, at some point our calcium is going to precipitate out. What in the world is the concentration of the magnesium when calcium begins to precipitate? All right. So, the way we start, we know our KSP for the calcium. Let's figure out, so we want to know what concentration is the solubility product, and this first is asking for calcium. So let's dissociate the calcium. So that means KSP equals concentration of calcium, concentration of hydroxide squared. So, make sure I get this right. Oh, this tells us our calcium concentration up here. There it is. I was like, I've got a calcium concentration somewhere. So you got to work this one first. So it tells us in solution 0.011. And we need to know our concentration of hydroxide. We know our solubility, 4.68, 10 to the minus 6. So let's take 4.68 times 10 to the minus 6 divided by 0.011. And now let's take the square root. So calcium hydroxide starts to precipitate out when the hydroxide concentration in the solution is 0.0206 molar. All right, now we go back and we use this precipitation equation. So we needed this hydroxide concentration because this is now our hydroxide concentration in the solution. So we know that our magnesium hydroxide dissociates into magnesium and also two OHs. And we know that our solubility product is going to be magnesium and hydroxide squared. In the problem above it, solubility product 2.06 times 10 to the negative 13. That's in the problem above it. I didn't just pull that out of thin air. We're solving for the concentration of magnesium. The concentration of hydroxide in our solution is now 0.0206 squared. So let's square that. And now let's divide the solubility product. Oh goodness. 2.06 10 to the negative 13th divided by that. So the concentration of magnesium is now 4.84 times 10 to the negative 10th. All right.